Yes, good. Good, right answer. But do you know by how much it will move? What does it depend on? It depends on the angle, yes? Okay. Can we quantify it? Can we say exactly the rate that it will move? So if we have basically here, so here it is basically full, here it is not. So the angle we move here, okay, I'll call it F, okay. If we have an angle theta, okay, we can say that it's going to be F cos theta, okay? So basically it's to do with the force that we exert and the angle as well. So the result is going to be F cos theta. That principle we can apply to electrical systems as well. Okay, so you're happy with this?
Yes.
Yes, excellent. So we can move on. Okay, but that is basically the principle. And that also applies to power factor as well. Okay, because you'll have heard of power factor. I mean, up there it says current, voltage and power. So I'm going to be talking about all three in my lecture. So, any questions before I start? That's the easy bit. It gets a little more complicated. No. Let's move on. Right, so what I would like to do today is to introduce you to three-phase systems. Okay, so the objective of the first part of this talk is to introduce the principles, determine the neutral current in a balanced three-phase system, and introduce star and delta connections. Star can also be called Y connection. Okay, you might see it as a Y connection because it looks like the letter Y. Okay. So, should be easy, I hope. But let's move on. Okay, so now the plug in the wall. Okay, is that three-phase? Hopefully not. Otherwise, I think there'll be a problem with it. That's a single phase. Okay. What we have, our three-phase systems, is systems that will be used certainly within this building. You'll get three-phase coming into this building, where it will be divided up into single phase. So, at home, if you live in an apartment block or you live on a street, it will tend to be split at a substation into single phases. Okay. But for transmission over longer distances, we tend to use three-phase systems. Okay? So that's actually combining three phases into one transmission. The reason we do that is it's more efficient. Okay? Does anybody know how much more efficient? Okay. It's probably maybe about 50% more efficient, I think. Okay? What it allows us to do as well is it gives us better power to weight ratio for machines. Okay? Because it's more efficient, it's more effective. We can use thinner cables. Okay? So it reduces the cost, the overall cost. And it also gives us a constant power delivery. Because one of the problems that we have in power distribution is we try and get balanced loads. The ideal is to have all the delivery on to balanced loads. The problems, or some problems that occur, is when loads are unbalanced. So there are various techniques that we can use to try and balance the loads. Balanced loads, I suppose, in a way are ideal. I'm going to talk about balanced loads because they're the most straightforward. If you want to read up more about unbalanced loads, that's fine. But the mathematics is a bit more complicated. So that's your choice. Okay. But I'll talk about the principle into balanced loads. So, three-phase systems much better than one-phase systems, certainly for transmission. Okay. Now, we can have more than three phases. We can have 4, 6, 8, 12 phases if we want, but they're not used. The reason for that is because we have a phrase, English phrase, law of diminishing returns. Have you heard of that before? It basically means more is not really better. Okay, it's not as efficient. Okay, so three phase is most efficient, and then you have reducing phase for 4, 5, 4, 6, 8, 12 phase. So 3 is best. Now, again, history. Does anybody know who invented 3-phase? Nikola Tesla. Yes. Okay, and that's why Tesla is used as an SI measurement, as respect to him. There were another couple of people who sort of were. They say invented about the same time, but Nikola Tesla is recognised as being Nikolai Tesla is recognised as being the person who invented the 3-phase. There are countries that do have 2-phase systems, okay, but most of the world will use 3-phase. And I'm happy to say that the 3-phase in Malaysia, I think, is the same as the 3-phase in the UK, certainly in terms of the colours. Okay. The colours changed in about 2009, in Malaysia, because it was the old RGB, and it's now grey, black, and I have it on a piece of paper. So, the reason that the colours are important is when you're connecting equipment to 3-phase, okay? Because if you don't connect it correctly, it will either not work at all or work in reverse. So, which can cause some problems. Some installers I know, they had the system where instead of sucking things, it blew things, and it caused a lot of problems. So that is something to be very careful of. Okay, so just some diagrams to represent the 3-phase voltages. That's basically our single phase, which is obviously it's our sine wave. I'm sure you're all familiar with sine waves, and go between 1 and -1. What we can introduce is we can introduce a second phase. So we've now got two voltages on that diagram, VA and VB. And just to sort of look at what we have within there, they have what is called a phase difference, okay? Because you know the full 360 degrees, yeah? Okay, so there you have that example, or 2 pi radians. If we arrange that the second phase is 120 degrees behind the first phase, that will then allow us to put a third phase in a further 120 degrees after that. So there we have, basically a delay of 0 for VA, a delay of 120 degrees for VB, and a delay of 240 degrees for VC. Okay? And it's that phase arrangement that gives the power delivery. Okay, it gives a nice constant power delivery. Okay, and then if we actually work out the phases, the representation, obviously, the instantaneous value is basically the big value at times sine omega t, or the RMS value there. And the notation that we tend to use here is that VA is basically voltage basically delayed by a factor of 0 degrees. B delayed by a factor here is because it's lagging is minus 120, and here a further 120, so it's lagging 240. If I say to you about leading and lagging, have you heard those expressions before? Voltage lead, voltage lag. If I draw do you understand what that means? And I'm not talking about civil engineering here. Okay, have you seen civil before? C is for capacitance, L is for inductance. Okay, so this is an easy way. If you have a capacitive network, the current leads the voltage. If you have an inductive network, the current leads the voltage. The current lags the voltage. So it's current leading for capacitance, current lagging for inductance. Okay. So it's important that, as I say, because that can make a difference whether it's current lead or current lag. So, as I say, it's important to recognise that. So we normally, as I say, represented by, here it's lagging is represented by a negative sign, okay, and leading would be obviously be positive. Okay, so just if we consider that these voltages are going to supply a balance load, we've then basically got that arrangement. There's going to be no, if it's a balanced load, effectively there's no lead or no lag. Oh, sorry, try again, sorry. For voltage to supplying a balanced load, there's no impedance. So we can basically look at the current lag there. And again, there'll be it's consistent. So I'll put those two together, because one of the limitations of this first arrangement is it requires 6 wires, okay, for the system. Now 6 wires is not very efficient, okay, so if we, in our 3-phase circuit, if we can reduce the number of wires, we can reduce the cost. So you find that standard 3-phase circuits don't use 6 wires. So the question is, are 6 wires necessary? The reason we use 6 wires is to combine the neutral points of the generators and loads together. Okay, like so. Okay, so there we've got our VA, VB and VC, and we've got our loads, our 3 loads there. Now, as I say, for balanced loads, we can connect the 2 combined points with 1 return wire. Okay, so this is our neutral. Okay, so I'm sure you've all heard of neutral wires as well. Neutral is not to be confused with earth, okay? But this is the neutral wire in our 3-phase arrangement. And for a balanced, let's just say balanced load, that's the arrangement. So we said 6 wires, are these 6 wires necessary? The answer to that is no, they're not necessary for this particular system. What we can have is we can have the return wire, or the neutral, can carry the sum of the phase currents. Like so. Okay? So that is a much more normal arrangement for 3-phase. So 3-phase is a 4-wire system. Okay? I mean, if you could always guarantee a balanced load in all cases, you could go down to a 3-wire system, because there would be no current in that bottom line. But practically, we will have a neutral wire somewhere. Okay, now I'm not, as I say, we've not got enough time, so I'm not going to go through all the maths. But the maths actually, we can work out the current. Okay. But we're using the trigonomic relations, okay, of cos A minus B and sin A minus B. Again, you'll have seen those before, and we know that A and B are those particular angles. Okay. So what that simplifies to is actually that the current in our neutral wire is equal to 0. Okay. There's lots of books that have this proof in there, so as I say, I'm not going through it today. But what we can say is that the current in the neutral wire is, as I say, is negligible, and in a perfectly balanced system it's going to be 0. The advantage of that, of course, is we can make it a very thin wire. It can be much thinner than the other 3 wires. So, as I said, in practice, the current in the neutral line is rarely 0, okay? But it's much, much smaller than the current in the other wires. So in a 4-wire 3-phase system, the return current is small and flows in the neutral conductor. Now again, drawing a little diagram. Again, my apologies. I don't think we can see any power lines outside the window. But again, in the UK, what we tend to get is basically system something. For power distribution is basically something like that. So the tower for the power distribution would look something like that. Is it the same in Malaysia? So, yeah. Okay. If you count, I was going to say you can probably just about see